Hello everybody, Justin Miller, Oxford College Physics here. We've got ourselves a nice little problem involving some tangential quantities, some centripetal quantities, and we're just going to look at some of this stuff. So here's the system. We're going to take ourselves a little point mass, attach it to some string, some light string, we don't kind of consider its mass, a distance of 0.75 meters away from the axis of rotation, and we're going to begin to rotate it with a constant angular acceleration of a 1.5 radians per second squared, and we're going to ask some stuff about it. So here's the problem. All right, so here it is. We've got a mass, 0.350 kilograms, the radius at which it is rotating about the axis of rotation, the angular acceleration, which is constant, 1.5 radians per second squared. It's initially at rest, and we are asked, how long does it take this object, this mass, to have a speed of 12 meters per second? Now that is a tangential speed, how fast it's moving through space. So part A, we just go ahead and get to it, right? We want to know when is v equal to 12 meters per second. That's the tangential speed there. So when does that occur? Well, again, we've got equation of motion for constant angular acceleration, and we can either deal with tangential quantities or angular quantities. In this particular case, we're already given the angular acceleration. Let's just use some angular quantities just because it's there. We've got ourselves that omega final is equal to alpha t plus omega initial in general, and then we've also got ourselves that v sub t is equal to r omega. So we can go ahead and get what omega final is in terms of what our final tangential speed is. So we've got ourselves that omega final is equal to v divided by r, which is our 12 meters per second divided by 0.75 meters. And let me just pop that in really quick. 12. And yes, of course, that is a 16.0. Meters cancels out, we're left with per second. Radians pops up because this is an angular quantity, and we got radians per second. So there's the equivalent angular speed with respect to the tangential speed being 12 meters per second. So now it's just a matter of when does that occur in time. What point in time? We can go ahead and take this, solve this out for time, and get that the time is equal to omega final minus omega initial divided by alpha. Omega initial is equal to a 0, so we are just left with 16.0 radians per second divided by 1.5 radians per second squared, which gives us a grand total of 10.667 seconds. 10.667 seconds is the time at which this little mass here will be moving at 12 meters per second. All right, that was fancy. Let us continue onward and see what else we can figure out regarding the system. So we've got a part B here. We want to know what is the centripetal acceleration after it has rotated around 10 revolutions. So, part B, we want ourselves the magnitude of the centripetal acceleration at delta theta is equal to 10 revolutions. Well, we know that the centripetal acceleration is just written a couple different ways. We'll just write it like this. That is r omega squared, or v squared over r. We'll use r omega squared. So there is the magnitude of the centripetal acceleration. It depends on the radius and the angular speed of this object. So the real question then becomes, what is angular speed after 10 revolutions? So we note that 10 revolutions is equal to 20 pi radians, right? 2 pi radians per revolution. So we've got this, and we've also got that omega final squared is equal to omega initial squared plus 2 alpha delta theta. One of the equations of motion for constant angular acceleration. which we can then go ahead and utilize to figure out, well, where's omega squared right there? We've got omega initial squared is, well, that's 0. So really omega final squared is just 2 alpha delta theta, which is this right here. So in terms of revolutions, we could write then that the magnitude of A sub c is equal to R times omega squared, which is 2 alpha delta theta. All right, so then we're just putting this in there with omega initial is equal to 0. And we can write out the centripetal acceleration as such. This quantity is that. So we quantify this out, right? We've got ourselves, the magnitude is then equal to 0.75 meters times 2 times 1.5 radians per second squared multiplied by 20 pi radians, which leaves us with a grand total for the centripetal acceleration of 5 times 2 times 1.5 times 20 times pi. 141.372. 141.372. The units of that, this is a linear type of quantity here. It is meters per second squared. So that is the inward acceleration that must be correlated with this object's continual change in direction when it is traveling at the rate that is substantiated by rotating around 20 pi radians under the action of an angular acceleration of 1.5 radians per second squared. All right, that was a good one. So what else could we ask? It looks like there's still a bunch of stuff here. So what's the total acceleration at t is equal to 13 seconds? So what do we know about the total acceleration? C. We note that the total acceleration is the vector sum of, well, the centripetal and tangential, which are perpendicular to one another. So really we've got this, the magnitude of the total acceleration is equal to the square root of the sum of the squares of a sub t and a sub c. So that is the magnitude of the total acceleration vector, and we've got the direction of that total acceleration vector gotten by the arctangent of a sub t over a sub c, and that is with respect to the radial inward direction. So this is what we're asked for. Magnitude and direction of the total acceleration vector at t is equal to 13 seconds. So what do we need to know? Let's expand this stuff out a little bit, right? A sub t, well, we know that a sub t is just going to be equal to r times alpha. That's all that the tangential acceleration is r times the angular acceleration. So that's constant. The time variance is in here because this is r omega squared, and omega varies as alpha t plus omega initial. So let us write this out a little bit different here. We can write this out then as this is going to be equal to r times alpha quantity squared, that's a sub t. And then we've got ourselves r omega squared quantity squared. All right, just in a couple little steps here. So if we've got, again, that omega itself is equal to alpha t plus omega initial. This is like an omega final, right? Well, that is omega as a function of time, so this really belongs right in there. So let us just go ahead and get this then. Omega final. In this particular case, probably easier just to quantify what omega final is and stick it in. So we can write that omega final at t is equal to 13 seconds is equal to our 1.5 radians per second squared multiplied by 13 seconds plus 0. And we get that the final angular speed of this object after 13 seconds, 1.5 times 13, yeah, 19.5. It's 19.5 radians per second. And then we can go ahead and quantify the rest of the stuff that we need. So, in a sense, all we need to go back is get what a sub c and a sub t is at that point in time. So we know that a sub t is constant, which is r times alpha, which is 0.75 multiplied by 1.5 meters radians per second. Breaking this up a little bit here. Switching the calculators up. 0.75. Just 1.125. Per second squared, and then we've got a sub c is equal to r omega squared, which is equal then to r to 0.75 meters times omega squared. Well, this is going to be omega at t equals 13 seconds, which is 19.5 back 19.5 radians per second. Quantity squared, which gives us 0.75 times 19.5 squared, 285.188, 285.188 meters per second squared. So something just to point out here that it is of some relevance, the centripetal acceleration is greatly greater than the tangential acceleration. Why? Tangential acceleration is constant. It's always 1.125 meters per second squared if we have a constant alpha and a constant r. But centripetal acceleration is continuously increasing because of the angular acceleration, increasing the angular velocity as time goes on. So they may start off to be around the same value under small amounts of time, but as time continues onward, generally speaking, the centripetal acceleration's value overtakes the tangential acceleration's value. So most of the acceleration is inward as the object speeds up more and more and more and more. At any rate, we've got this for the tangential and centripetal acceleration values here. So we can go ahead then and get ourselves that the magnitude of the total acceleration is then 1.125 meters per second squared, quantity squared, plus 285.188 meters per second squared, quantity squared. Yeah, it's going to come out really close to 286. We'll just put it in, just for argument's sake here. We got 1.125 squared plus 285. 285. Quantity squared, square root, 285.19. 0.19 meters per second squared. So really, if we just rounded this off, we get approximately the same thing. It's a little bit more than just the centripetal acceleration. There's the magnitude of the total acceleration at t is equal to 13 seconds. What direction is this acceleration? Well, got ourselves that theta a total. Again, the arctangent of the tangential divided by the centripetal. And it looks like it's going to be really close to zero because it's mostly radially inward. But we've still got ourselves the arctangent of 1.125 divided by 285.188. And tangent 1.125 divided by 285.188. And that's about 0.226 degrees. All right, so overall, we got magnitude and direction, and this again is with respect to the radially inward direction. With respect to a sub t, a sub c, excuse me, centripetal acceleration. All right, that was some fun stuff right there. Took a little bit of unraveling, but not too bad, right? Just keeping track of the tangential versus the centripetal quantities. Always going back to equations of motion for constant angular acceleration. That's a great. So let us move on then. Part D asks, what constant velocity would substantiate a centripetal force of 170 newtons? Ultimately, that's what it asks. So we go ahead and proceed with this. This is a D. If the magnitude of F sub c max is 170 newtons, that is, if the maximum centripetal force that this string can withstand or build up to substantiate is 170 newtons, what is the maximum speed, tangential speed, that this mass can have? So this is only looking in terms of centripetal. We'll make a little differentiation here momentarily, but let's just answer this, right? So what do we got for the centripetal force? And that can be written as mv squared over r. So we can solve this out for v, right? That seems pretty straightforward. We've got ourselves that v then is going to be equal to the square root of f sub c r over m, which is then equal to the square root of 170 newtons times 0.75 meters divided by a mass of 0.350 kilograms. And we get ourselves a Vmax, speed through space, which would substantiate 170 Newton centripetal force acting on this mass, as 170 times 0.75 divided by 5. Get ourselves 19.086. 19.086 meters per second. So once the mass is moving that fast, that is a centripetal force, the inward force, that must be acting on it to continuously change its direction and ultimately produce this circular path that it's maintaining. So we are asked in part E, what time does that occur at? What time does this particular speed occur? Which is ultimately asking at what time is the centripetal force 170 newtons? So we've got an E, T is equal to a what? Well, there's a couple different ways that we could go about this again. Let's use some of the tangential quantities. V, right? We've got ourselves that V sub t final is equal to a sub t times t plus v sub t initial. The final tangential velocity is equal to the tangential acceleration times time plus the initial tangential velocity. So really, this is just an old equation of motion that we've used before. I'm saying specifically tangential now. So let's get rid of some of this stuff here. And what do we get out of this? Well, we need to know, number one, that V tangential initial is equal to 0. Objects initially at rest, the initial angular velocity is 0, thus the initial tangential velocity is 0. So we need to know what a sub t is, right? A sub t is equal to r times alpha, which we've already computed, 1.125. We'll just do it again. This is going to be equal to 0.75 meters times 1.5 meters per second squared. Equals 1.125. Let's make it sure here. 0.75 times 1.125, good. 1.125 meters per second squared. So there's the tangential acceleration. And, well, here is our final velocity. V tangential final is to be 19.086 meters per second. So, with this expression right here, for tangential velocity as a function of time, we solve that out for time. We know that this is equal to a 0, and we've got ourselves the time at which that occurs is then going to be the tangential final divided by a sub t, which is then 19.086 meters per second divided by 1.125 meters per second squared. 2.06 16.965 16.965 seconds. So we start this object from rest. Spin it faster, faster, faster. And at some point in time, well, after 16.965 seconds, the centripetal force exerted on that mass via the string, via tension in the string, right, is going to be equal to 170 newtons. So that's it. So here's one last question here. What if, talk about the total force acting on this particular mass, and say that it's actually the total force that can only build up to only be 170 newtons. When does that occur? When is the total force 170 newtons? Well, just like the magnitude of the total acceleration is the vector sum of the tangential and centripetals, so is the total force. We've got some tangential force, which is responsible for the angular acceleration, and we've got some centripetal force, which is responsible for the centripetal acceleration. So we can really resolve this down into looking at those accelerations, the total acceleration itself, and extracting out at what time that substantiates a correlated a correlated total force of this. So let us do this. So this is just to get the centripetal force. You should find if we add in the tangential force that is responsible for the tangential acceleration, the total force being 170 newtons will occur at a time less than this. Now it's probably not going to be a whole lot less, but it's going to be a little bit less. Let's see how many significant figures we get here. So when is the total force equal to this? Well, let us first go ahead and say that the total force, the magnitude of the total force, is equal to the magnitude of the total acceleration. We'll just say m times the magnitude of the total acceleration. Why do we do this? Well, because it's going to be easier just to look at that total acceleration and correlate it with this. So with this, we've got ourselves 170 newtons, the magnitude of the total force divided by 0.350 kilograms is equal to the magnitude of the total acceleration that correlates once again with the total force being 170. So we've got 170 divided by 0.35 gives us 45.714. 485.714 per second squared. All right, so there's the total acceleration. Correlates with this being the total force. Ooh, number looks a little familiar, right? Except this was 882. Anyways, it's really close to some other centripetal acceleration that we're looking at. All right then, so we want to know, when does this occur at? T equals what regarding that? Well, again, the magnitude of the total acceleration is equal to the square root excuse me, of some of the squares of the tangential and centripetal. The tangential is constant, the centripetal has time variance in it. What happens if we just go ahead and start making some correlations here? I'm going to make life a little bit easier and not do this completely symbolically, because having some numbers here will be just helpful in this particular case. So we got 45.714 meters per second squared is going to be equal to the square root. A sub t, we've already figured out that that is 1.125 meters per second squared. That's just r times alpha. And then we've got a sub c. Well, a sub c is going to be equal to r times, just put omega squared for right now, quantity squared. All right, so this is what we've got working with right now. Let us go ahead and we start trying to isolate this, because this is what has the time in it, right? Omega has the time variance. We want to isolate omega, and then we can figure out what time that omega is occurring at. So let us square both sides. So we can write this as the quantity of 45.714 meters per second squared, quantity squared, is equal to 1.125 meters per second squared, quantity squared, plus r omega squared, quantity squared. That looks fun. We can subtract that from both sides, which isn't going to change this by that much, but we'll just go ahead and do it, right? So with this, I'm going to leave this up so we can do a little comparison. I'm going to take this value, and I'm going to take this value, and we'll just subtract them. Yeah, let's do this. I'm going to rewrite things a little bit. We can write this as r omega squared. This is quantity squared. Is equal to 485.714 meters per second squared minus 1.125 meters per second squared. We could take the square root of both sides. That would be good. We can take the square root of both sides, and then we can divide by r. And then we can take the square root again. Oh, that sounds pretty fun, huh? So we can write this, that omega squared is going to be equal to the square root of this, 485.714. Dropping the units right now, they're getting in my way. 1.125. That whole quantity divided by r is equal to omega squared. So let us quantify that. I think that's going to be the easiest thing to do at this point, without having too much craziness to put in the calculator. So I'm going to get a value for that. And we've got the square root of that squared minus 1.125. Minus 1.125 squared. That divided by 0.75. So this comes out to be 647, 6173, 647.6173. All right, and that should be radian squared, second squared. This doesn't really belong. Yes, we're good with that. Radian squared per second squared. Meters cancels out. Radians pops in, and then we can take the square root of that, giving us that omega is then equal to 25.4483. 25.44833. I'm adding on some more significant figures. Let's see how close we can really get here. This is radians per second. And how do we get t out of this? Well, we know that omega final is equal to alpha t, right? Plus omega initial. Omega initial is equal to 0. So we can divide this by alpha, giving us that t is then equal to omega divided by alpha, which is the 25.44833 divided by 1.5. Radians per second squared, or radians per second, squeezing it in. Oof. Let's see what we get out of this. And answer divided by 1.5. 16.965. 16.96555. Sometimes if we're looking at problems where a sub t is not much less than a sub c, you get that there is some very big difference between the time at which the total force and the centripetal force are the same values. So you gotta be careful with that. In this particular case, enough time's gone by. That's a good problem, right? I agree. All right, have a good one. Till next.